All right, let's take a look at the answer to this clicker quiz. The correct answer is this one right here. And why is that? That's because the order at which each of these reactions reaches their peak concentration will determine the order of the reaction. So since G is at peak concentration right there, we know that one's got to be first. Then E reaches peak concentration right there, that's got to be second. And then F reaches peak concentration somewhere out over there. So therefore the correct order should be G, E, F. Now let's take a look at the steady state approximation. It's going to make us approaching these sequential reactions a lot easier. And later on when we get to reversible reactions, the steady state approximation is going to come in real handy at that time as well. So let's write down again the rate law for each of these steps. This step doesn't change. This step is not affected by the steady state approximation. And that's no problem because the solution to this one is easy enough. We saw that on the last slide. It's this step now that we're going to be making the approximation. So the rate of change of B. And I'm going to write down what that is. It comes from A and then it disappears depending on what the concentration of B is. And here's the steady state approximation. It assumes that the rate of accumulation of B is approximately 0. And this will be true if K1 is relatively slow or a small number and K2 is relatively fast or a large number. That means that B doesn't have a chance to really accumulate very much. So if that approximation is true, then we can just immediately write that K1 times the concentration of A equals K2 times the concentration of B. All right, and then that allows us to just say that the concentration of B equals K1 over K2 times the concentration of A, but then we can just plug that expression right in there. So the concentration of B becomes K1 over K2, starting concentration of A, e to the negative KT, like so. Okay, let's write down the rate law expression for C, finally. This becomes just K2 times the concentration of B. But we know what the concentration of B is right over there, so the accumulation of C, or the rate of C, just becomes K2 times K1 over K2, and of course those just cancel out. Starting concentration of A, e to the negative K1T, like so. So another way to write this is just that, well, the solution that we get is that C becomes starting concentration of A 1 minus e to the negative K1T. And that's the solution we get, much simpler than the one we got in the previous video for these sequential reactions using the steady state approximation. So now we're going to consider one more type of elementary reaction step, not a sequential reaction, but a parallel reaction. So that's what this one would look like. There's a reactant A, and then in this case, there's actually two possible products. We can call them B and C. And we're going to call Kb the rate constant for the formation of B, and Kc the formation rate constant for the formation of C. Don't mix Kb up with Boltzmann's constant. I'm not talking about Boltzmann's constant in this case. I know we use the letter K for about 5 different possible applications. So let's write down the rate law that we get from this. So we know that A is going to be changing concentration because it will be forming 2 different products, and each of those products depends on a different rate constant. So we're going to have 2 terms in our rate law. We'll have some of it disappearing along the pathway that leads to B, and then also some of it disappearing along the pathway that leads to C. Both negative because A is what is being taken away out of the system. And we can just combine these together to form an expression like so. All right, and then what about B and C? Well, we'll write those down right now. It's going to be a positive number for B, depending on the concentration of A, and C also positive, depending on the concentration of A. Notice that when I'm forming these rate laws and writing down what they are, I'm using the rate constant for the given step, and I'm using the reactant that there was for that step, because the rate at which a reaction proceeds along a step is going to depend on the concentration of the reactants. So that's how I'm able to construct all of these different rate laws. And we know the solutions to this reaction, and I'm just going to write them all down right now, and we'll take a look at them. So there's the solution to the rate law for the changing concentration of A, and it's a lot like a typical first order reaction. So we were able to write it down using a first order reaction type expression like that. So now next one is the concentration of B. There's our changing concentration of B with time. Notice that it depends on how quickly A is disappearing and also on these other rate constants. Lastly, we'll get to C. So there is the solution for the concentration of C. Notice that it looks exactly like the one for B, just with the symbols B and C flip-flopped around. Now, the whole reason why I wanted to show you this was because I wanted to demonstrate the ratio between the changing concentrations of B and C. Now, if you plug in those expressions for B and C, and then you cancel a whole bunch of things out, you're left with a very simple expression. The rate constant of the formation of B divided by the rate constant for the formation of C. This ratio remains constant as the reaction proceeds forward. So that's fairly interesting. We can use this now to talk about the yield of substance B. And what do I mean by the yield? Anyone who does organic synthesis or synthesis of any sort knows of the common phenomenon of producing unwanted byproducts. So if we have reactants A and some forms B and some forms C with different rate constants, then we can just call B the desired product. And we can call C the goo that you make on accident when you do organic synthesis. And we may want to calculate what's the yield of B. It turns out that that yield is whatever the concentration of B is as the reaction proceeds over the total concentration of both the desired product and the goo. And if we know the rate constants, then we can just predict that yield directly. So if you can construct your organic reaction to have a relatively high rate constant for the desired product, you're going to get a much better yield.